All right, hey everyone. So I had some requests for homework 6 solutions since those topics might show up on the midterm on Wednesday. So I thought I would work through homework 6 here and just look at a solution for it. So there's two questions. The first one is doing more I/O stuff, and the question is to basically um, check pin 6, and if pin 6 is high, increment file register 80. So to do that, we look at the data sheet, and pin 6 is RB2. So we want to look at RB2, which is port B, bit 2. And we want to continually read that bit, and if that bit is set, then we want to increment file register 80. So we need to do some setup first. Include. So do your usual include p18f1220.inc. Let's start at origin 0 and move LW 7F, move WF, add con 1. So that's the usual, set up everything to be a digital port. And then trisB, we want to have look like this. So this is RB012. We need that bit of trisB to be a 1. And we don't really care what these other bits are. The easiest way to do this might just be to say, move LW FF, move WF trisB. So all port B bits are inputs. That's a safe condition. And in fact, the initial value of trisB is in fact all ones. So if you look at your data sheet where it describes the special function registers, and you look at trisB, we'll see the initial values are all ones. So that's the do no harm condition. All of the bits are set to be inputs. So technically we don't even need to do this, but it's nice to be explicit and mark these things. Alright, so now we're going to have a loop. And remember, our requirement is if pin 6 is high, then we want to increment the register. So we want to read port B. So move F, port B, comma 0. So our W register is the contents of port B. Now, we don't care what's in these positions. We only care about what's in this bit position. And so this is where a bit mask will come in. So I'm going to say AND LW, and I'm going to AND with the following mask. Right? Now by ANDing with this mask, whatever this bit is, when I AND with a 0, I'm going to get a 0. And this bit, when I AND with this 0, I'm going to get a 0. All of these bits are going to get zeroed out when I finish this AND operation, except this bit right here, right? So port B looks like this. And then if I AND with this, I'm going to end up with the following. Right, I end up with an 8-bit number, zeros everywhere except right here. So I'll AND LW with this mask, which is 0x04. So keep RB2. And now there's two possibilities. If the result of this AND is 0, then RB2 was equal to 0. If the result is this, then RB2 was equal to 1. So if the result of ANDing is 0, then RB2 was a 0. So I can just say branch of 0 loop. And if the result of that AND is 0, it means pin 6 was low. So if I don't branch, pin 6 was high, and now I want to increment file register 80, so I can say increment file register 80. And here I can say, RB2 is high, and then I can branch back to loop. And so there's a program that will accomplish the goal of question 1. All right, so question 2, we've got a set of code, and we want to do 2 things. Write down the program counter, the address in program memory where each instruction is stored, and then after each call and return, show the contents of the stack as well as the value of the stack pointer and the top of stack registers. So I've got a copy of the program here, and let's figure out the location in program memory first. So here's the address in program memory. Well, origin 0 says the next instruction is stored at location 0. Increment takes 2 bytes, so the call is going to be at location 2. Call takes 4 bytes, so the next instruction will be at location 6. Origin 20 says the next instruction goes at 20. Increment takes 2 bytes, so the next instruction is at 22. Call takes 4 bytes, so the next instruction is at 26. Origin 30 says the next instruction is at 30. Increment takes 2 bytes, so the next instruction is at 32. So there's the addresses in program memory. So program memory addresses. And now for each call and return, we want to see the stack pointer, and the top of stack register. And it's after the call. So after the call instruction, our stack's going to look like this. We don't know what's in location 0. Location 1 contains the address of the next instruction, the location to return to. Right? The call is at location 2. The next instruction is at location 6. So this is going to contain 06, stack pointer equals 1, saying that's the last thing we pushed on the stack, and the top of stack registers are going to contain 6. So top of stack low will be 6, top of stack high will be 0, top of stack upper will be 0. So TOS upper equals 0, TOS high equals 0, TOS low equals 6. All right, well, we make a call to 20. We come down here, we have another call statement. So after this call, what does our stack look like? Location 0 is still unknown. Location 1 will still have a 6 in it. But this call will increment the stack pointer to a 2, and then at location 2 it will store the return address of the next instruction, which is 26. And top of stack will be 26 because that's what the stack pointer is pointing to. Alright, so then we jump down to location 30, we do an increment and we do a return. So after the return, location 0 is still unknown, location 1 is 6, location 2 is 26, but after the return, the stack pointer is equal to 1. Top of stack is just what's at location 1, which is 6. So the only thing that's changed in the return is the value of the stack pointer. And then after this return, right, currently stack pointer is 1, so after this return, stack pointer will be equal to 0. Top of stack is effectively undefined, and the stack still looks like, unknown 6 and 26. So I would not write it like this on a homework assignment. I would write it out on multiple sheets, and I would just, spell out in words. After the call at location 2, stack pointer, top of stack. And then on a separate line, I'd say after the call at location 22, and list this, and then after the return at 32, list this, and then after the return to 26, list that. But that shows you the expected values. So calls push the address of the next instruction onto the stack, and returns pop the stack, which simply means decrement stack pointer. So that's the set of values you would see for question 2.